Hey everybody, welcome back to Young Engineers of Today. I hope you had a good weekend, and I hope you're ready to finish off model rockets, because that's actually probably what we're going to be doing today. This is going to be a fairly short lesson. Um, we might have a little bit more material. Awesome, glad to hear it, Liam. Uh, nice, so you got a brand new shiny computer. Um, we might have a little bit more material to cover on Wednesday after this, but really we're kind of reaching the bottom of the information repository that we have planned for model rockets. Oh, naturally. Um, so, like I said, this is actually probably going to be a short class. I went through all the material that we had, and I couldn't really find anything else that was related enough to cover um, that we haven't covered already. But that might change with time. But anticipate that we're probably going to be covering a new topic on Wednesday. So you have that to look forward to in case, model rockets haven't been your jam. But it seems like it's a pretty popular um, subject, at least for those it is popular with. They're very vocal about it. Now some of you might be silently sitting there going, "Well, model rockets, blah." But if that's the case, well, fear not. Come Wednesday at the earliest and next Monday at the very, very latest, we will be going over something new. Yeah, blah. It's a noise of frustration. So, without any further ado, why don't we go ahead and get started on this, like I said, very short lesson. Chances are very good that we're going to be ending decently early today. Um, so, enjoy that. We'll have a nice relaxed class today as we go over this stuff. So rocket launching. This particular one is actually about launching rockets. Things to consider on and before launch day, and sort of finishing up the parts of our theoretical rockets in order to get a better idea of how they fly and stuff like that, and actually determining how high they fly, things like that. So we're going to go over like the size of the launch site that you'd need, anticipating how high your rocket is going to go, and actually determining how high your rocket goes when it's launched. So that's what I mean about things to consider on and before launch day, because you're going to want to consider these things when you're launching rockets. But yeah, so now we've seen much of the design philosophy that goes into creating a model rocket, why you want to pick particular fin shapes or engine sizes or, recovery systems over others, nose cone shapes, things like that. But how does a lot of this fit together, and what do we do on launch day? How high can we tell our rocket went? What about how wind would affect things? I mean, that's a lot of questions. We don't really go too in depth about how wind affects the rocket, because that's a lot of math work that is far, far beyond the scope of this, and it also requires some element of science or prescience, omniscience, I suppose, because we'd have to know exactly how fast the winds are going on that day, and how they buffet the rocket and things like that, which is sort of stuff that is hard to anticipate and calculate anyway. Most rocketry design and stuff like that goes into minimizing the wind's effects rather than trying to anticipate it and work around it. So that involves checking weather reports to see if it's going to be windy and not launching that day if it's going to be too windy. Things like fins and streamlined designs in order to minimize the amount of how much the air affects the rocket, stuff like that. So it is important to note that air will always affect the rocket trajectory, and wind especially so. So wind will always make your rocket fly at least somewhat laterally, sometimes, in fact, a lot of times, further than you anticipate. And we'll sort of touch on that a little bit later. But for that reason, you would need to figure out how much of an area you'd need for your rocket to launch, because you want to make sure that you're not going to fly into like buildings or land on people or land in the freeway or something like that. You don't want it to land in trees. So you want to make sure that you've got a sizable enough clearing for your rocket. that should not be there. Goodbye. There we go. Um, this right here is a bit of a small diagram to provide a sort of baseline for a minimum launch area for a rocket. It's small and hard to read, but basically just understand this. So each area here represents a different class of motor. The smallest square here is quarter A or half A. They both share the same area. And you got A motor and B motor and C motor and D and E and F and G. They just get larger and larger. So at half A and quarter A, you can see maybe here that each side is 50 feet in length. So it's a 50 by 50 foot area, which is an area of 2,500 square feet, which is not small, but it's not, huge either. Thing about square feet and area and stuff like that is that number tends to get fairly large quickly, which is why when we're talking about larger areas, we use larger units like acres and square miles. When you use square feet, generally that's just in reference to the size of houses and things like that. So 2,500 square feet is actually, I think, about the size of my apartment, now that I think about it. So a 2-bedroom, 1-bathroom apartment. Now you just got a some more insight into my life than you probably anticipated. So if you live in a house that's got like a few bedrooms and a couple of bathrooms and stuff like that, chances are, oh no, that's bigger than my apartment. Chances are the living area of your house, if it's, let's say, 3-bedroom, 2-bathroom, is probably about the size of a launch area for a quarter A or half A rocket. So it's not an insignificant amount of area. Imagine you take all the rooms and you place them together in as close to an approximation of a square as you can, and that's about what you're dealing with. Now, on top of that, the math isn't exactly perfect here, but it's a decent rule of thumb that for each engine class you go up, you double the length of the sides. So half A and quarter A are going to be 50 feet, whereas an A class is going to be 100 feet on a side, a B class is going to be 200 feet on a side, a C class is going to be 400 feet on a side, and so on. So Class A engines need at least a 100 by 100 foot area, or 10,000 square feet. Class B engines need 200 by 200 feet, or 40,000 square feet. Which you can also see how this gets out of control really fast. 40,000 square feet is a very large area, though probably smaller than you would anticipate. Like, I would say that a 10,000 square foot area is probably about the size of a small athletic field for a school or something like that. So like your elementary school probably had like a field in the back for playing around in and stuff like that. That would be about 10,000 square feet. 40,000 square feet, well, as the school gets larger, so does the athletic field required. So that would probably be like a high school athletics area, field and all. So it's sort of hard to imagine in your head when you start getting into numbers this large, which is part of the reason why we have math to express the size of space and stuff like that, because it's just completely incomprehensible to our monkey brains. But at least we have hard numbers to work with and this kind of thing. But also notice how you quadruple the size of the area with each doubling of the sides. And that's just math. You have math to thank for that. Because if you're multiplying two sides together, if you double the length of both of those sides, you end up with 4 times the area. If you can just imagine like a square of a certain size. If you make that square double, oops, look at this square. So if you make that square about double the length, you see each of these sides is about double the length. You see you can fit 4 squares in there. So 4 times the area. Look at that wonderful diagram. That was amazing. But it's important to keep in mind that this area I've been telling you about, this is a minimum. It's a fairly safe minimum, but it is a minimum regardless. And it is a lot of space. And we're going to need more space if the wind is actually blowing that day. In fact, if it's blowing enough, it's oftentimes a very good call just to say we're not going to launch today because the wind's blowing too hard. Because it will get blown too far off track. You'll run into an issue where you can't, recover it because it's blown into a tree or something like that, or it's blown so far away you don't actually know where it's gone. So you want to make sure that the wind isn't blowing too hard on a launch day as well. On top of that, the higher the rocket goes, the more it is affected by the winds. Generally, you get faster winds higher up. On top of that, if the wind is blowing, it's blowing along a very large vertical area. It's not just blowing at human level. It's also um, the wind is still blowing up at like skyscraper level even. So if the wind is blowing a fair amount as the rocket is going up, it is just being hit by wind constantly and therefore going further and further off course. Um, so that's another reason why it can be important not to launch on too windy of a day. Because if your rocket is going fairly high, like if you have a fairly beefy engine on that rocket, your wind is going to become the bane of your existence. So you want to have an idea of how high your rocket is going to go as well. So we already looked at Open Rocket, which gave us a pretty decent idea of how high the rocket would go, but it's also good to have a general idea of how high a rocket might go based on its engine class. So good news, there's actually a general rule as far as height is concerned when considering motors. Now, this next diagram I'm going to show you is a best case scenario sort of thing. So, take it with a grain of salt. But here's a set of general altitudes that different classes of engine can achieve. Now, like I said, they're best case scenarios. Right here, Class A is listed as 475 feet in height or 145 meters. And if you remember from Open Rocket, a lot of times that Class A rocket that we built wasn't going to reach 145 meters. Like we were looking at 130, sometimes even sub 100, depending upon the situation. I think the sample rocket we built, it actually ended up just a little bit below 100 meters. So this is almost kind of too optimistic. But by the same token, it also gives us an idea of a sort of worst case scenario as far as dealing with the wind is concerned and stuff like that. So, if you anticipate, for instance, if you build a Class F rocket and you anticipate it's going to go about 1,200 meters into the air, you can you would be safe in assuming that, and you would actually probably do all right launching on a windier than recommended day because the rocket won't actually go as high as that projection. So, for that reason, it won't actually get blown as far off course and stuff like that. So you could, in that sense, you would actually be a little bit safer by anticipating your rocket's going to go higher. You would be not quite over-engineering, although that is sometimes a term that is used for stuff like this. If you're launching a Class A rocket, you don't need a triple chute system with a drogue chute and all kinds of stuff. In fact, that would be, that would be amazing for slowing the rocket down, assuming that everything had enough time in order to properly catch and decelerate the rocket. But it's unnecessary, and in fact, it would end up harming the rocket because the weight of the parachutes themselves would negatively affect the height of the rocket. And you would have so many chutes that you couldn't necessarily guarantee that they'd all get deployed in time for the rocket to stop. So that can be an example of over-engineering. But I digress. As you can see here, the rocket heights actually go kind of, sort of, at a linear rate. It definitely slows down a lot as they get larger. Then there's definitely a spike at E, but then it slows way down again. Um, so it's sort of important to note that on top of that, if you're planning on building as large a model rocket engine as possible and slapping it into the rocket, you're also going to get diminishing returns. Um, you're going to have a greater jump in height from uh, B to C than you are from C to D, that kind of thing. Almost, sort of. Oops. So when we're talking about like these maximum heights and stuff like that, I think I already touched on it, but I'm sure you guys have some reasons as to why those rockets probably wouldn't get as high as those estimates. Why do you think that's the case? Yeah, definitely. Um, the rocket could be higher weight than the models that they use in order to get those numbers. Um, what else? Yeah, that's another one, definitely. There could just be more surfaces for drag. Maybe you stuck an extra fin on there, and the drag is enough that it actually the rocket loses like 10 meters in altitude. Um, it could be, you know, the nose cone has a flaw on it, and there's like a small eddy of air that's created, and suddenly you've lost 15 meters in height. It could be that the way that you've glued the fins onto the rocket body, there's a whole bunch of there's a like it's a very messy glue job, and there's a whole bunch of glue just sort of globbed on there, and that creates drag, and suddenly you've lost 20 meters in height. Stuff like that. Those sorts of things actually have a surprising effect on the rocket's ability in order to gain height. So the rocket could be heavier than anticipated. Um, the drag could be more than anticipated, stuff like that. Like it can be quite difficult in order to reach those maximum heights because you need a rocket that is basically specifically engineered, um, very specifically engineered in order to reach those sorts of heights. So that's an excellent question. I don't know because a lot of those dimples on golf balls are made in order to let it go further and also increase its stability while it's flying, as I understand it. So I couldn't tell you. Um, but although I think the reason why it works for a golf ball is because a golf ball is a sphere and the dimples make it spin, and in spinning it, it helps to increase its stability. Just that again, I'm working off very hazy memory here, but really, they tested it on a car and it made it more fuel efficient. Huh. I haven't seen that Mythbusters episode. I should see that. Apparently, they put dimples on a car and made the car more fuel efficient. Yeah, aerodynamics definitely. Um, hmm, you learn something new every day. Wonder if we're gonna have cars with dimples all over the place in 20 years. It's gonna be like the first aerodynamic car, and it's gonna look like a friggin' golf ball. Everybody's gonna get used to that, and they're gonna look at old cars and they're gonna be like, man, either that looks ridiculous or that's a timeless design, and I really wish we could go back to that. But yeah, this is part of the reason why we spent so long trying to figure out what kind of fins you might want on your rocket, because um, that kind of stuff is a very big determinant in how high your rocket goes and how stable it is and things like that. So we know now that rockets won't necessarily reach their maximum height, and in fact, it is quite difficult for them to achieve their maximum height because rockets have to be very carefully engineered in order to be able to do that. So how do we figure out how high our rocket goes in reality? As you can see, this is quite a short presentation. Um, So we got a very simple way of determining rocket height. We basically just have a single person on the ground some distance away from the launch site with a tool that has a weight attached on the end of a string, and it's called a clinometer, like incline. So how does that work? How does a person standing on the ground with a weight on a stick, or excuse me, a weight on a stick or a weight on a string, how does that, yeah, you got it, Brandon, but so how does that follow? Well, a clinometer is nothing more than a weight on a string or a stick attached to a site in front of a paper or a piece of sheet metal or something that has some markings on it. And those markings are degrees, angles and degrees. And the user stands on the ground and watches the rocket or the tree or the building or whatever they're measuring through the site, like look at the top of it. And then the string or the stick will point at a set of marks determining the angle. They'll point at a particular angle. And whatever it points at, this is the angle that this clinometer has relative to the ground. So if you're to draw a picture like it is here of this person raising it up, this is inclined, hence clinometer, a certain angle from the ground. We assume, of course, the ground is flat, so it's not always going to be a completely fair comparison. On top of that, there are a couple of other things that can mess with it, which we'll get into in a moment. But it gives you an angle on one end. Now, why is that useful? Well, notice how the person here, the launch site, and the rocket all create 3 points for a triangle. Look at that triangle, beautiful triangle. You might be going like, why triangles? Well, it just so happens that we have a whole lot of math that we can use to find the sides of a triangle. Whole lot of math. Nice work, me. So note this equation to the right. We have tangent, and then we have this weird symbol. That symbol is referred to as theta. It's actually a Greek letter. So tangent of theta is equal to height divided by baseline, and then we kind of wiggle things around, and we get height equals baseline times tangent of theta. Okay, so what is the tangent? Well, the tangent is the correlation between the adjacent and opposite sides from an angle on a triangle and the size of that angle. What does that mean? Well, basically, it is the ratio of lengths between the side adjacent to the angle and the side opposite the angle. So if we were to place the length of the opposite side over the adjacent side, we'd get some number, like say this is 4 and this is 5, we get 0.8, and that would be our division. Now, tangent is actually just a numerical relation that a lot of people a lot better at math figured out before I was even on this earth. However, it always holds true. So if you can find the tangent of this angle right here, it will be 0.8. So the tangent of the angle will be 0.8, and the length of the opposite side over the length of the adjacent side will also be 0.8. Because if we have a right triangle, we can figure out the length of any of the angles that we want, or excuse me, the length of any of the sides that we want, if we just have one side and one angle, of course, aside from the right angle. That's part of it. If you don't have a right angle, you would need to know two angles and one side, or you could know two sides and one angle. There's actually a whole thing on that. But anyway, in so doing, we can figure out the lengths of all of the sides of the triangle, and we can figure out the sizes of all the angles, because you've got tangent, which is for opposite over adjacent. You've got, well, here's the other thing. This last side is referred to as the hypotenuse. The side that's opposite the right angle is always referred to as the hypotenuse. Using the sine of an angle, you can find the relationship between the opposite side and the hypotenuse. Using the cosine, you can find the adjacent side and the hypotenuse, and using the tangent, you can find the opposite side and the adjacent side. On top of that, you can work it out backwards, so you can get a relationship between the opposite and the adjacent, and then get the inverse tangent on it, and then get an angle. But here we have a side and we have an angle. And the reason we have a side is because we simply measure how far away that person is from the launch. So they go out and we're all like, okay, so you're gonna go out 100 feet from the launch pad, and you're gonna stand there, and they measure it out. Just make sure that they're at 100 feet, and that person would stand there and watch the rocket as it's launching, and they'd use their clinometer. By doing that, we would have the adjacent side, and we'd have an angle. So that brings us back to our equation here. The height, or this last side, is equal to the baseline distance, the adjacent side, times the tangent of the angle created by the clinometer. By doing that, we get the height. And here's the great thing. I mean, tangent is something that's just, deriving tangent is something that is far beyond the scope of this class. In fact, it's far beyond the scope of most math you're going to take. And it doesn't really even need to be done, because it's already been done so many times. However, the nice thing is, again, a lot of people, it's like a function. It's a whole bunch of stuff. But a lot of people, a lot smarter than me, sat down and just basically created a whole table of values. And they programmed it into calculators. So if you have an angle, if you want to find the tangent of it, all you need to do is reference a table or plug it into your calculator and press the tangent button, and you get a result. And then you can multiply that result by the distance of the baseline. And then you get the height of your rocket. Kind of cool, right? Like, by knowing how far away we're standing from a launch site and knowing how far we're tilting upwards in order to look at a rocket, we can determine how high that rocket goes. Now, it's not going to be perfect. What sort of things could mess with that? Yeah, user error on the instrument. Definitely. You could be misreading the instrument. You could be holding it incorrectly. What else? Think about how that rocket's flying and what could go wrong with that. Yeah, if it flies towards you, it's going to seem higher. Likewise, if it flies away from you, it's going to seem lower. Exactly. So, I mean, despite our best efforts, this rocket still flies in 3D space. So if the rocket flies directly towards us, well, not directly towards us, but like over our heads, you're going to have to tilt the clinometer up further in order to be able to look at it. So it's going to artificially inflate the height of the rocket. Likewise, if the rocket flies away from you, you're going to have to tilt the clinometer probably down a little bit or keep it in the same spot, even if it is going up, in order to keep it in the sights, which makes it seem like it's not going as high as it actually is. So it's not a perfect measurement system. It generally, that sort of measurement system works better with stationary things, like, landmarks and buildings and trees and stuff like that. But it's still a totally possible and viable means to measure how high a rocket goes. And it certainly gets you within the ballpark of the rocket height. So, it's not like you throw it out and it's totally useless. Now, there are other methods. You could use two people and have them both measure the height, and then it's going to be the ratio between their distances and the angle that they point at the rocket, and it's a whole much more complex thing, but it would be certainly more reliable than this. But this is perfect for something like, if you guys were to launch rockets in the lab. Having a single person measuring height would be just perfect for your purposes, You're not trying to do any sort of, aerospace engineering or anything like that. This is just sort of a fun means of figuring out how your rocket designs will affect rocket height and stuff like that. But yeah, so there you go. There's the other thing. Rocket design, rocket launching, all that stuff. I'm not going to lie to you. There's quite a bit of math involved. In fact, I mean, let's just back out of that a bit and be a little bit more general. There's a lot of math and engineering, and hopefully this is starting to drive that point home, because everything we've done has involved at least some form of mathematics, whether it's geometry or trigonometry or calculus or something like that. Now, you guys may not know this stuff yet or all of this stuff yet, but if you decide to pursue engineering, you'll definitely become much more familiar with those subjects. It's just simply unavoidable. If you start doing computer science, you're going to get discrete math, and if you start doing electrical engineering, you're going to be doing discrete math and also linear algebra and calculus and physics calculus and things like that. If you start doing like mechanical engineering, you're going to be doing a whole lot of calculus, because there's going to be heat dissipation and movement and things like that. You're going to be doing a whole lot of geometry, things like that. So all I'm saying is, it's not necessarily going to be easy, but don't despair. If I can explain it to you, even if it doesn't make a whole lot of sense now, it's more like, if I can explain it, then you guys can figure it out. You guys will be able to power through that stuff. It just requires, dedication. And persistence. But yeah, just so you know, if you want to get into engineering, you can't really escape the math. The two are basically just intertwined and linked together forever. It's always going to be there. You're always going to have to deal with math. There, as you get further along and engineering tools get better, there are going to be a lot of programs and stuff like that that can do a lot of the math for you, but you're still going to need to know the underlying concepts and why you use particular sets of math and stuff like that. And if you're ever creating those programs for other engineers to use, well, then you're definitely going to have to be very familiar with the math that goes into that particular branch of engineering, which, if I know anything about engineers, it's a lot of them tend to create the tools that they need for their particular branch of engineering on the computer. So a lot of them at least learn one programming language enough to be able to create a program that they can use in order to simulate the stuff that they need to simulate. Even if there's something out there that already exists, just because sometimes it's fun to do. But anyway, I think that's actually going to do it for today. Like I said, very short class. If we have any more material to cover, we're probably actually going to cover that on Wednesday very shortly before we move on to the next subject. Just because if there wasn't enough today, there's definitely not going to be enough on Wednesday in order to cover an entire class. So that's just how it goes sometimes. But hopefully this will be a good opportunity for you guys to get caught up on anything that you need to do in life otherwise, and just be able to take an easy day, relax a little bit, have an additional day that you don't have to worry about all sorts of extracurricular stuff. But yeah, so I'm going to go ahead and do the poll questions, and then we'll leave it open for question and answer time. If you guys have any questions about anything, obviously I'm going to be here because we've got plenty of time. But otherwise, once we're done with the poll questions, you're more than welcome to head out. Have a wonderful couple of days, and we'll see you on Wednesday.